If someone asks you, what is the fastest programming language in the world? Some will say C++, the veteran king, operating systems, game engines, databases, all its territory. Some will push Rust, saying it has zero-cost abstractions, safe and blazing fast. Even Linux kernel and Windows are adopting it. Others will bring up Zig, saying it has no hidden control flow, no macro magic, and its compile time is as clean as a scalpel. Online, there are countless benchmarks about them. Some measure loop speed, some measure sorting algorithms, some measure matrix multiplication, and some measure HTTP concurrency. Every test produces different results. So, who is the fastest? In fact, this question itself is asked wrongly, because what truly determines the speed of a program very often is not the programming language at all. It is the compiler, the CPU, and the way you write your code. First, we need to get one thing straight. The CPU never executes C++, nor Rust, nor Zig. The only thing the CPU can recognize is machine instructions, binary encoded machine code. So no matter which language you use, their ultimate fate is the same. The source code goes through the compiler, generates machine code, and finally hands it over to the CPU for execution. What actually runs is not the C++ program, but the machine code generated by the compiler. Then why are C++, Rust, and Zig generally all very fast? The reason is simple. They all belong to ahead-of-time compiled languages. Before the program even runs, the compilation phase has already finished the vast majority of optimizations, compiling directly to native machine code. Unlike Python, which needs an interpreter translating every line of code into bytecode on the fly at runtime. Unlike Java, which needs a virtual machine and has to spend time warming up after startup, letting the J compiler gradually optimize. Nor like JavaScript, which needs to guess while running at runtime. Hot functions get compiled. Cold functions stay slow forever. These compiled languages are different. They natively run close to the metal, and their performance ceiling is inherently high. What's more interesting is that you write a trivial function, say, returning the sum of two integers. Implement it in C++, Rust, and Zig, respectively, and then open the compiler's assembly output. You might be surprised to find that the final generated machine code could be exactly the same. Because for the compiler, what it sees is not a language label, but a piece of logic. Given the same logic, there's only one optimal machine code sequence. So the gap in many benchmarks is simply not caused by the language. Then why do online reviews always claim that Rust is a bit faster, or Zig is a bit faster, or even C++ is faster? The reasons usually come from several other places. First, the compiler itself. C++ is not just GCC. There's also Clang MVC and Intel's ICC. For the same code, GCC with O3 and Clang with O3 may generate completely different instruction pipelines. Some compilers are good at loop unrolling, repeating a for loop 8 times to reduce branch jump counts. Some compilers are good at auto-vectorization, turning single instructions into SIMD instructions, processing 4 floating point numbers at once. Others do link time optimization, LTO, which can inline functions across files and even eliminate the overhead of virtual function calls. So what you see is actually the gap in compiler optimization strategies, not the pedigree of the language. To go even further, even with the same compiler, different versions can have performance differences. Second, the implementation of the standard library. Take strings as an example. C++'s standard string has short string optimization. Strings shorter than 15 bytes are stored directly on the stack. No heap allocation needed. Rust string does a similar optimization. But their capacity growth strategies differ. C++ typically doubles the capacity, while Rust grows by roughly 1.5 times, which directly affects the frequency of memory reallocation. Copy semantics also differ. C++ copies strings with deep copy by default, while Rust's move semantics transfer ownership by default. Even the underlying allocator is different. The default is the system allocator, but you can replace it with gmalloc or memalloc, and performance might immediately improve. So when you run a benchmark, what you are actually measuring is the design of the library, not the core language. Third, memory and cache. Modern CPUs have clock speeds up to several gigahertz, but memory latency is tens of nanoseconds. That sounds short, but to the CPU, it means hundreds of instruction cycles of waiting. If the data is already sitting in L1 cache, the CPU can get it in one cycle. If it has to fetch from memory, it may wait for 200 to 300 cycles. So what really slows down a program is often not the computation, but whether the data is sitting in the cache in time. For example, traversing a two-dimensional array. If you traverse row-wise, the memory is contiguous, and the cache hit rate is extremely high. If you traverse column-wise, each step jumps a large stride, the cache frequently misses, and the speed can be 5 to 10 times slower. So data layout is often more important than the language itself. Fourth, CPU microarchitecture. The same machine code, when put on Intel and ARM, can perform completely differently. Because modern CPUs do not mechanically execute instructions one by one. They execute out of order, do branch prediction, speculative execution, and even prefetching and auto-vectorization. If your code better matches the CPU's execution habits, for example, branches that are easy to predict, like those with clear loop counts, then it runs blazingly fast. So what actually affects performance is also the CPU itself. What about Rust? Many ask, doesn't Rust's ownership checking and borrowing checking have runtime overhead? The truth is exactly the opposite. Rust's ownership system almost all happens at compile time. When the program runs, those checks have long disappeared. The CPU has no idea what ownership or borrow checker means. What it sees is still just ordinary machine instructions. Rust's zero-cost abstractions are no joke. Its iterators after compilation are as fast as handwritten loops. Its generics, via monomorphization, expand into concrete types without runtime dispatch overhead like virtual functions. So Rust can guarantee memory safety while still being firmly in C++'s performance tier. That is its most impressive feat. And Zig. Many people like Zig, not necessarily because it is faster, but because it is more transparent. No implicit control flow, no macro magic, no operator overloading fog. What you write is almost exactly what the compiler generates. Moreover, Zig allows you to execute functions at compile time with the comtime keyword, computing constant results at compile time and embedding them directly into the machine code. This predictability itself is an important foundation for performance optimization. So after all that, now you know the answer to the question, C++, Rust, Zig, who is the fastest? What really determines speed is actually the algorithms and data structures. Is it a hash table or a red-black tree? Is it ON or ON squared? How is memory organized to keep data close to the CPU? Is the data contiguous or fragmented? Are you accessing row-wise or column-wise? Which compiler did you use? What optimization level did you enable? And did you do PGO? Can your code make the branch predictor happy, keep the vectorization engine fed, and keep the out-of-order execution unit busy? The language itself is merely the container that carries these decisions. Understanding this is the real beginning of understanding program performance.